Thank you.
All right, thank you, TD. And thank you all for joining. So just to get us a little more familiar and also help us to tailor this conversation, how many of you have heard of blockchain technology before? Okay, most of you, great. How many of you are in financial services? Okay, fair amount. Supply chain or manufacturing? Okay, healthcare? Other. All right. Okay, well, I'll talk to you others later. So we're going to talk about a few things today. First, why the blockchain and analytics. And since there's some of you who understand a blockchain, we'll quickly go through that. Bryan will speak to the blockchain data complexity and tie in, and that leads into the existing challenges that we have today. He'll go through a new approach, and then I'll wrap up with what to look for, and a demonstration and some use cases before we go to Q&A. So just a little background on who we are. We're a blockchain web services company. So in a quick tagline, we're like Amazon Web Services for blockchains. This is a partial list of our customers. We have thousands of companies around the world using our technology, and they use us to create, very quickly, blockchain applications. So those applications are at the top there in the financial services world. These are just a few of the examples. We are at the middleware or services level, and that means we support and are blockchain agnostic for all of the underlying protocols of different types of blockchains, whether it's Ethereum, Bitcoin, or other blockchains. We provide 3 types of blockchain web services for our customers: identity, web services, transaction, and analytics. Since we're at the Spark conference today, we're going to focus more on the analytics, but I wanted to show you this to give you context for why we have the type of data we do. So in a nutshell, what BlockCypher allows companies to do is outsource and future-proof their blockchain applications so they can come to market faster and at much less development cost. So why the blockchain and blockchain analytics? Now, 3 quick reasons. Not everything is a blockchain use case. Not everything should be using blockchain technology. So these are 3 quick reasons why and when you recognize a good blockchain use case. So first of all, there's a need for decentralized transactions. And I'll give you a use case for this. International payments. Today, if you were to send money from here to Africa or some other country without a well-built-out banking system of rails, you'd have to spend potentially up to 10% of the transaction in fees, and it could take weeks to get there. Now, with the blockchain or using blockchain technology, that time is cut into minutes or less, and the cost is 1% or less. Second reason why you would use a blockchain is for increased transparency. Now, for many industries, we'll take supply chain as an example. You are sending literally spreadsheets around to track, say, the shipment of certain goods or the movement of certain things from one place to another. Now, with the blockchain, because everybody has a copy of that ledger, you have that full transparency. And you're no longer saying, hey, did you mean to put that decimal point there or that comma there? Because you have that transparency from the beginning. And the last reason is security. So blockchain offers increased security, and that means not only for authentication and authorization of individuals, but also because you have these distributed ledgers, you don't have this situation where everyone could basically cut off access to this main database and then everybody's hosed. So why blockchain analytics? Now, if you've been watching the news around blockchains, there has been massive market adoption of not only Bitcoin, but other cryptocurrencies. So right now, we are at $100 billion in market cap for cryptocurrencies. Banks, just a few months ago, when we were at the 30 billion mark, were saying, someday, when cryptocurrencies have a market cap around 100 billion, the banks will start getting interested. So that time is now. And very clearly, the FDIC and a number of other countries around the world are seriously analyzing and figuring out what their blockchain strategy is and around regulation. Now, what does that mean for analytics? And I took some of these points actually from a recent DTCC report that came out earlier this year. So there's blockchain and there's this power of the blockchain, and cryptocurrencies are growing very quickly, but the challenge still remains in data searching, high-speed access to data for analytics, and some of the fundamental issues around the analytics. And for that level of detail, I'm going to hand it over to Bryan to talk more.
Great. Thanks, Karen. So I want to talk about some of the more technical underpinnings of some of the properties that Karen has described. The design of a blockchain like Bitcoin may seem bizarre to people who are primarily accustomed to centralized applications, but it's precisely these strange properties that allow blockchains like Bitcoin to solve a very specific problem, which is how do you create a useful, decentralized, and resilient network? So what do I mean by these properties? By a useful network, I mean a few things. It's founded on cryptography to provide concrete, resilient, and secure ownership of tokens. We have a monetary policy, including things like inflation control and fraud prevention, built right into the network itself. And we have a powerful scripting language that allows developers to extend things further into things like multi-signature or smart contracts. Now, what do we mean by a decentralized network? By this, we mean that no peer needs to trust the result of any other peer's computation. Any claim, regardless of who sends it, is independently verified by every single fully validating node on the network, regardless of who sends it. And as a result, regardless of the actor, there's no requirement for trust between participants in the peer-to-peer network. Now, what do we mean by a resilient network? For this, we mean that the network as a whole is capable of reaching a single convergent consensus state, even in the presence of a significant number of purposefully fraudulent actors. In distributed computing, we call this the Byzantine generals problem. Bitcoin, like every proven public blockchain, utilizes a system called proof of work in order to address this problem. By forcing any actor attempting to update global state to perform a tremendous amount of computational effort and using a system of economic incentives and disincentives for attempting to mess with this global state, we're able to create a system that can probabilistically arrive at a single convergent state without the need for any kind of global coordinating layer. Now we have a system that's capable of arriving at consensus, but there's still a relevant question of what are we consenting on? And the answer is a global transaction ledger. Here we have a schematic of a transaction. It's got some set of things called inputs. These are consuming previous funds that have been produced by transactions elsewhere in the system. And we have, it produces a set of what are called outputs, which are funds that are available for later consumption. So we take each of these transactions is independently verifiable, and we take a set of them that are themselves consistent within each other and package them together. We cover this with a header, which includes our hash, which is our proof of work target, some metadata, and most interestingly, a previous hash. Now this construction right here is what we know as a block. The previous hash pointer points at the previous block in the chain, and so on and so forth, all the way back to a very special block known as Genesis, which is the previously agreed upon starting point for the blockchain. And as a direct result, we have an independently verifiable chain of the entire transaction history stretching through from the very beginning of the instantiation of the chain until now. This is how a blockchain gets its name. Now, inputs and outputs are the system of currency or funds within these blockchain systems. An input always consumes a single previously generated output, and a transaction is a many-to-many mapping between inputs and outputs. Within inputs and outputs, we have a chunk of code known as script, which is executed by all fully validating nodes to determine spending authority, or who is able to spend what funds. Ownership identifiers in Bitcoin are traditionally addresses, which are most commonly owned by a single entity. These are derived from the public portion of an ECDSA public-private key pair, but sometimes it's something else, like a representation of a not yet exposed script. Now, it may seem like we have a pretty straightforward identity system, and as a result, behavioral analytics can be pretty straightforward. But there's a number of confounding technologies that conspire together to make things much more complex than they may initially seem. For example, we have a technology called hierarchical deterministic wallets, which allows a single master private key to participate in the trivial derivation of a nearly unlimited number of child private keys. Each of those child private keys has an associated public key and therefore address, but from an outsider's perspective, these addresses have no discernible relationship, and it's actually provable that it's impossible to determine which addresses belong to the same HD chain. And as a result, a single user can orchestrate thousands of addresses as if they were one. There's also a technology which is used throughout the network that's known as pay-to-script hash, in which your output is paid not to an ECDSA public key directly, but to a script itself. And so here we have a snippet of script. The actual contents aren't terribly important, but what's happening is we're packaging 3 identities, 3 public keys, each with their own individual addresses. They're being packaged into the script, but what's exposed on the network is not those addresses themselves, but the hash of the script and an apparent address that has no relationship to A1, 2, or 3. And as a result, the participants in this scheme are not revealed until this output is spent at a later time. This brings us to the status quo. The current tools that are in use around the network are lacking. Law enforcement agencies still overwhelmingly use manual investigation and traversal when attempting to do forensics tasks involving criminal investigations into Bitcoin and other blockchains. Traditional tools lack the flexibility to evolve alongside Bitcoin's ever-changing technology and usage patterns, and that's where we hope that behavioral analytics is going to bridge the gap, where we can focus on patterns of movements and behaviors of individuals rather than properties on a transaction or address level that are easily manipulated. At the end of the day, you need a solution that can encompass multiple forms and multiple layers. Each of these components has their advantages and disadvantages, but none of them individually is able to capture the level of intelligence required to derive the insights that we're looking for. While the rest of this presentation is going to focus more on machine learning and graph traversal, as that's obviously the topic of interest here, one thing I want to emphasize is that it's important not to discount the importance of human intelligence. Some components, for example, this address found here that begins in 1 bones, these are immediately recognizable to any person that participates in Bitcoin as the address of a gambling site known as Satoshi Bones. And yet, because of the relative rarity of these so-called vanity addresses and the high chance of false positives, these aren't a suitable target for machine learning or other kind of heuristic-defined techniques. And so it's very important to remember what humans have in terms of human intelligence. So first thing I want to jump into is how we're representing the graph. Throughout this presentation, I've talked a lot of relationships that form directed graph structures. And so here we have a snippet of an address-to-address graph. So addresses, remember these are the derived public portions of ECDSA key pairs, are the nodes on this graph. The edges here are the transactions that encompass movement of money between these nodes. And what we see here is the visually striking distribution of funds from a single actor to participants in a mining pool scheme. Because of the way that relationship information is encoded on this graph, it's possible for even the untrained human eye to discern this very complex relationship. And this is one of the things that makes directed graphs so powerful. But not all graphs are created equal. Because of that transformation to the address-to-address graph that I showed on the previous slide, there's a great deal of loss of resolution, and there's assumptions that are being baked into the graph itself. This is fundamentally a projection from a very high dimensional data set into a lower one. And so you will always be losing dimensionality when you do that. And this is especially true when you look at something that's built on Spark. Because Spark employs this vertex cut technique within GraphX in order to distribute nodes and edges throughout the cluster, you have to be very conscious of what your nodes are, what your edges are, and how data is encoded within them. The consequence of this is that your operations are going to vary dramatically in terms of parallelism and data locality depending on where you put your data. Now here's a brief summary of some of the graph types that we utilize in our analytics system today. As you can see, they are all fundamentally different. They have fundamentally different endpoints or nodes. They have different edges, and they encompass different relationships. They also have very different properties. And as a result of this, not all of them can be used for the same types of analysis, and not all of the same techniques can be applied to each of them. And so we have to be very careful in how we're interpreting graphs and how that we understand the repercussions of the particular graph that we choose for a particular type of analysis. So why would you consider to build a system like this on Spark and GraphX? The most obvious answer is to look for something like a single node database like Neo4j, which gives you a lot of advantages in terms of startup time and speed. But we found a lot of advantages with the Spark and GraphX approach. We have one infrastructure that that serves our graphs, machine learning models, and computation together. We have access to our graph properties extremely natively and at an extremely low level when we do our machine learning training, for example, things like in-degree. And we have horizontal compute and storage scalability for when our solution needs to grow further. Now I want to talk a little bit about our machine learning component that derives insights from our graph and structured queries. Here's a brief Venn diagram describing a little bit of the things that I thought were going to be an issue when I started this project versus what actually ended up being a problem. There's not a whole lot of overlap. It turns out that the things that you think, that I thought overwhelmingly were going to be an issue, things like algorithm selection or tuning of hyperparameters, ended up taking a backseat to the things on the right, which were overwhelmingly data-driven issues, or understanding the data that you have. For that reason, I have a bit of a simplifying recommendation, which is to start with unsupervised methods and iterate when you're on your machine learning pipeline. That's not to say that unsupervised methods are better. You will end up with a supervised method. But an unsupervised method removes the architect's expectations from the data pipeline at a very early stage and allows the data to speak for itself. As a result, you get a lot of very nice advantages. You have faster ramp up, fewer parameters to tune, less overfitting risk, and you honestly get to evaluate the null hypothesis, which is very important when you're starting a new project from scratch. Like I hinted at before, it all begins and ends with data. No matter what machine learning algorithm you choose, there's going to be a beginning portion that looks a lot like this. You're going to have a myriad of data sources that are going to come together. You're going to extract your features from those. You're going to select, transform, and scale those features before they're handed off to any kind of machine learning algorithm. The feature extraction component on that last picture is a lot harder than it looks. There's a lot of questions around what features to include and how do you balance the risk of overfitting with your need to capture the relevant parameters. And for that, it's very helpful to look at the variance of the variables and how they correlate to the result that you want. If you introduce this mindset every time you do your feature engineering, you'll find that it exposes a lot of issues that may come down later. For example, when a feature demonstrates the same underlying relationship in multiple ways, which may unfairly bias your results in ways that you don't necessarily intend. Now, in the blockchain world, blockchain data is only one part of a larger picture. We have our raw blockchain data that's on the order of 100 gigabytes. It's, I think, a little bit more now. It grows at a rate of about 6 megabytes an hour. And that actually only ends up being a minority of the data that we utilize. We're fusing this data with node data that we're collecting, network and transient data on the peer-to-peer network, as well as derived data, denormalizing the combination, and we end up with a data set of about 1 terabyte. Bigger graphs need a lot of tuning, and I've hinted at some of these edge and vertex distinctions before because of the vertex cut technique that GraphX employs. But you also have to consider your partition strategies, or where your edges and your edge data are actually located within your cluster, as well as considering data denormalization and how are you baking relationship data down into features, into numerical data, and where is that data being stored. Blockchain data in particular has some interesting nuance. Global consensus follows the chain with the most work. You can simplify this as the longest chain of blocks is the current consensus. And as your view of the network changes and as more information is introduced, that may change. And so if your analytics system can't tolerate this kind of arbitrary rewrite of history, you're going to need a solution. A processing delay can address virtually all of your rewrite cases. This is something that's guaranteed by the proof of work algorithm. But it tends to hinder your real-time analytics efforts. And for that, we turn to something called the Lambda Architecture. So here's a brief schematic of a Lambda architecture. We have our real-time input flowing in from the left. On the top, we have a non-real-time process. It's batching this transaction information in this particular case. It's being sent to a machine learning pipeline, and it's training a machine learning model, which is getting pushed down into a data store. At the same time, that identical real-time input is flowing without delay, undergoing the same feature extraction and data transformation steps as the top portion, and being tested against a slightly older version of the machine learning model, generating results in near real time. The reason this works is because the aggregates that your machine learning models are tracking fundamentally are very slow to move. And so your loss of accuracy, as long as you maintain this consistent level of delay, is relatively small. And your accuracy of your results should remain very high. So I want to walk through an example that we built alongside the Department of Homeland Security as part of a contract last year. We built a pipeline capable of clustering different transaction types together as well as detecting anomalous transactions. I'm going to refer back to this Lambda architecture, but first I'm going to focus on our batching, our non-real-time process on the top. As I said before, a delay in processing can address virtually all of your blockchain mutability concerns. If you imagine a timeline moving to the right with encompassing blockchain data, on the top we have our non-real-time process. We have an artificial delay to capture some of the rewrite probability. We have our fairly significant machine learning processing latency, and then we have our trained model, which covers some history that extends off to the left. But that same trained model is being used all the way into real time, allowing us to do real-time analysis. Now, we begin with feature extraction from live node data. We're taking our transaction, we're extracting about 20 features out of it. This is being fed into a k-means pipeline. We're using a Cassandra data store to back this. And so we're pulling the latest transaction batch, extracting, scaling, and then updating our machine learning model all within Spark. And we have there's a nice feature of machine learning pipelines in Spark 2.0, which gives you pipeline persistence. So we can take this pipeline and we can store its metadata and its parameters down into the data store itself. And we can ensure that when we reuse this pipeline or sub-portions of this pipeline, that those parameters remain in sync, which is critically important as you iterate on your machine learning pipeline. And so when we pull out our feature extraction, our feature scaler, and our machine learning model interface, and we're testing it against our streaming input, we're using this to derive real-time transaction type and anomaly results for alerting purposes. But we're also using this for coloring our graphs, our directed graphs, for more efficient traversal decision making as well as graph analysis. And now I'd like to hand it back to Karen to talk a little bit about use cases and maybe give a little demo.
Okay. Thank you, Bryan. Bryan just came back from Korea, so we're very happy he's here with us, and he's recovering from a cold. So thank you, Bryan. Just to summarize, what to look for in a blockchain analytics solution. First, an infrastructure to ingest and transform the metadata, a multi-layered solution like Bryan discussed, graphs that address multiple purposes, resources for tuning these graphs, and real-time analytics. Now, what I want to go into a little bit next are some of the use cases. And to highlight what a use case that Bryan mentioned before, we've been working with the US Department of Homeland Security. So we started with one award with them last year. We've continued to work with them on a second award, and it's specifically to understand and come up with a blockchain analytics solution, as well as look at specific new blockchain protocols that are more obscure, and I'm trying to obfuscate basically who the addresses belong to. Now, why is this a problem for the US Department of Homeland Security? Well, ransomware is a big problem, and existing approaches tend to be more reactive, follow the money. Whereas our approach, being proactive, is focusing on identifying anomalies. And so to just give you an example of how this works, we'll show you some visualizations. And this is a visualization through Tableau, which I'm sure most of you probably recognize. But this is starting with our data. And like Bryan described when we discussed before, that because we have been serving so many companies with many different types of blockchain web services, we've been capturing a lot of data for these different activities, for these different purposes, applications, but also putting that blockchain data together with other data. And other data then allows us to come up with origin, country, latitude, other geographic data. Now, what makes that interesting then is when you look at a dashboard, for example, you can now start to see certain trends over time, focus on, say, an anomaly, which is that high point there, see where the transaction origin is by country, but also by type of software. And use that information now to develop these patterns to understand the behaviors that you can use to track and basically highlight future anomalies. Now, using that information, you can go back and then follow the money when you have a transaction that looks particularly bad. So here you can see how you can drill down on a particular address, follow the path for that address all the way through, and start to understand more of what's going on. And these are the tools then that financial institutions, law enforcement, and others would use. Now, given the time that we have left, I'm happy to go into more detail on some of the use cases, but I don't think we actually have too much time for that today. So I encourage you to either come speak to me afterwards or come to our website where we have a number of these use cases that you can download and look at in more detail. This time, I'd like to open up for questions since we only have about 4 minutes left before your hungry bellies direct you someplace else. So anybody have any questions? I think the mics are over there.
Either you can take the mic on the other rail, or I can give you the mic here.
What kind of clustering are you using? Like a k-means or hierarchical or density-based?
So for, okay, my mic's still on. For that particular example that we demonstrated, we were using k-means clustering. We are also experimenting with various classifiers for supervised classifying methods for slightly different use cases.
Yeah, thanks
There's
for
a question back up there. Oh, yeah, sorry. Yes,
Is that me?
you in the blue, right. Thank you.
Yeah, I was really interested by this talk. I was wondering if, in terms of fraud detection, if you think there would be a benefit, or I don't know, maybe there already is, to having a database of these known fraudulent or attacker accounts. So I know in other industries, a lot of times they share a database because it's sort of in everyone's interest. Is that going on, or is that?
Yeah, so we are sharing, and so for law enforcement in particular, we've been working with some threat analytics companies to share this information. So for the recent WannaCry event, we've been sharing information with them, and yeah, just collecting all that and sharing that back with law enforcement.
Is that
so there are some.
Sorry, is that in a public database, or is it sort of on an ad hoc basis?
Yeah.
So at this point, it's still in the early days. There are a couple of attempts to do more industry-wide efforts. For example, the anti-phishing working group is working on developing ransomware-centric data sets. But I think the most prominent actors in the Bitcoin space in particular, it's been on a more ad hoc basis specifically. And part of the challenge here, especially when it comes to Bitcoin financial crimes, is because of some of the technologies that I hinted at where people are able to cycle through addresses more quickly. It's not necessarily an issue of which addresses are bad or which on-chain identifiers are bad. It's more of we have a new identifier or a new address. Can we determine, is it the same party as a previous party? Is it behaving in a fraudulent or malicious way? And so that's where we're looking at more of the kind of, I guess you could call it softer machine learning behavioral analytics.
But what you're asking about is an area that is definitely developing, and so we've been part of a number of different alliances, different consortiums to build up that knowledge.
Awesome. Thanks.
Hi, nice talk. So, how many features do you have for k-means model?
For that particular use case, we're looking at individual transactions. So we found that the sweet spot was around 20 for that one. It was a relatively small data set, relatively low dimensions.
So in your production, there are only 20 features?
Sorry?
I mean, in your production, in your real environment, the k-means model only have 20 features?
Yes, in that particular use case.
Oh, okay. All right. Thank you.
So, all right, that is the last question for now. We are pretty much run out of time. Please join me in thanking the speakers.